In this one, we have got a cosine squared of n, that's an n, and it's all over n squared plus 1. Well, I'm just going to cut to the chase on this. We could do either the comparison test in this case, but we know that the top is going to be less than 1, right? So cosine squared of n is always going to be less than or equal to 1. So I can say that this whole thing is less than or equal to 1 over n squared plus 1. By adding 1 to the denominator of something, you make it smaller. So I know it's going to be smaller than 1 over n squared. Well, that's just a p-series, and that is greater than 1. So this converges, because in the p-series we want that exponent to be bigger than 1, and 2 is, so it converges. This one here, we can write this in sigma notation just to get a handle on it. This is just simply 1 over n to 2n minus 1, right? Those are going up by odd numbers, going up by 2's, hence the 2, and then the minus 1 adjusts it back down to 1, 3, 5, 7. Classic odd number thing. So what's going on here? Well, we can do this with an integral test easily. We could also simply think about it by comparison. I think that I'll just do one more of these by the integral test. And in this case, we've got a function, f of x, that's equal to 1 over 2x minus 1. So then the integral of this will be from 1 to infinity, and it's 1 over 2x minus 1 dx. Well, what is the integral of that? That is going to be, looks like it's going to be a logarithm, ln of 2x minus 1. But when I take the integral of the derivative of the inside, I'm going to get 1/2. So then this is going to be the limit, and let's go as t goes to infinity, and this is going to be evaluated then from 1 to t. So then I just get the limit as t goes to infinity of 1/2 ln of 2t minus 1, and then when I plug in 1, I get minus the ln of 1, which is 0. So really, what happens to this? Well, as we looked at before in our handy sheet of growth rates, we know that ln of p, of course, is going to go to infinity as you get n, or in this case t, going to infinity. So if this goes to infinity, this is divergent. Okay. Again, you have that suspicion because we know that 1 over n, right, that diverges. And if we're doubling the denominator, that's going to be smaller, so it'll be underneath something that's divergent, but it's only underneath by a numerical amount. So it should feel as though that makes sense, that we shouldn't just be able to take infinity and cut infinity in half and have it somehow be a finite sum. Alright, so on to this one. Now this is getting to where we talk about error. We're supposed to consider this series, which is going to be 1 plus 1 over 2 to the 4th is 16, plus 3 to the 4th is 81, plus 4 to the 4th is 16 squared. That's 256. So that's getting big. I'm going to stop there. But I know that when I go, they want us to do S10. So that means the first partial sum, or the partial sum for the first 10, is going to be all this plus 1 at the end with 4 zeros up to 10,000. All right. So pause the camera, get the calculator, type that in. Alright, back, turn that on. That's what I got. If you can see, I've got 1 plus 1/16 plus 1 over 81 plus that is 3, then 4, 256. Oh, I put that out of order. That's funny. I guess I did that. I did 4 and then 5, and you'll see I inverted them by just raising them to the -1. Anyway, I got 1.08203653. That's way more decimals than you need, but there they all are. Okay, now the error, that's the important thing. The error is going to be the integral from 10 to infinity of this, 1 over n to the fourth. Okay, and I'm going to convert that to function notation because I should, and that's dx with integral. So we are pretty good at these sorts of things. We know that if that's x to the minus fourth, then it's going to go x to the minus third. When I bring that out, it's got to be a minus 1/3, and I'm going to evaluate this from 10 to infinity. And I am going to cheat a little bit because that should be too, well, alright, I'm not going to cheat. I cannot do it. Limit as t goes to infinity, and then that is, of course, up to t. Well, what happens there? Then that becomes the limit as t goes to infinity of minus 1/3 t to the minus 3 minus then a minus 1/3 t to the 10th. Okay, well, as t goes to infinity, that drops out, and I get minus that, so it's just 1/3 t to the 10th. And that would be then to the minus 10th. So that is just 1 over 3 with 1, 2, 3 zeros. We would obviously not expect that to be in the numerator. That would be a crazy error. Okay, so that's the approximate error. So that would be approximately equal to 0.0003 repeating. All right. Then there is an improved method, and the improved method is worth spending a little bit of time to think about. I think the book does a pretty good job, but I think it needs some explaining. And that is that if we have something that is decreasing like this, and we stop it, I'll stop it like there, say visually, and so suppose that's our sum up to our 10th term. All right, and we're trying to get a sense of how much are we missing out here, okay? Because that's what we did with this. We integrated from 10 out to infinity to sort of figure out what this is. Well, what we're doing is we're taking this value, 10, and we're finding out to 11, say, and then out to 12, and then out to 13, and out to 14, and out to 15, like that. So we've got all of this accumulated extra amount, which we've decided is 1/3000th. What we can also do then is we could say, well, if we skip that and go to s, the partial sum at 11, and figure out what that is out beyond, then we can go somewhere in between, because like we found with Riemann sums, that if I look at this amount here, and if I sort of think about bringing it over, shifting it over, what I've got is that moved over to here, and then by averaging these two, it's a little bit like we're splitting the difference. We're finding how far is it to this middle line. And so the way we express this is we'll say, well, there's the sum that we got from S10, and then we'll add to that the integral from 11 out to infinity. Well, that's going to be the lesser amount to the truth, and that's going to be less than the S10, sorry, the sum for the first 10, and then plus when I integrated from 10 out to infinity. The difference here is that this is 10 and this is the 11. Well, I do the same thing with the integration with our 1 over x to the fourth, but I go 11 out to infinity. When I find that, which guess what, is going to be 1/3 11 to the minus 3. That is going to be my lower estimate of error. So let's find that out real quickly. So that is 11 caret to the minus 3. Oops, it didn't like the negative, sorry. and then I divide that by 3 because I'm taking 1/3 of it, and I get 2.5043. I'll stop there. Then 1, 2, 3, 4. So I've got this amount here and this amount there, and basically you just average those, and that gets you the amount that is closest to your sum of your first 10. All right. So final thing will be to get an error that's within 0.00005. So I do the same sort of thing. I just do 1/3, then x to the minus 3 is going to be less than 0.00005. All right. Well, I can write this as 1 over x to the third, and I can swap places with this, so this becomes 1 over 3 times 0.00005, and that's less than x to the third, and then I just take the cube root of that, and when we do that, it is 1 divided by, in parentheses, 3 times 0.12345, close parentheses, and hit enter, and then I raise that to the third 1/3 power, 1 divided by 3, and I get 18. So it would take me 18 steps to get out to a degree of accuracy that is within that tolerance that they want. All right, there's a lot there. Good luck. Bye-bye.